Hello, and thank you for joining us. I am Jasmine Navarez, Digital Content Coordinator at Simulations Plus. I'll be hosting today's webinar behind the scenes, making sure we don't have any technical difficulties. In this webinar, Becky Graves, our Director of Simulation Studies, will walk you through PBPK best practices and explain how you can leverage the first-in-human simulator to build PBPK models to translate non-clinical data to accurately design your FIH clinical trial and beyond. Peter Kilford, our Associate Vice President of Software Business Development, will serve as our moderator today. A few housekeeping items before we begin. We take your privacy rights seriously. By registering for and attending this event or participating in the Q&A session, you are allowing us to contact you for follow-up. You may ask questions via the questions panel on your dashboard at any time. If you need assistance, please use the hand raise icon. We'll address all the questions in the Q&A after the presentation. Before we begin, I'd like to conduct a quick poll just to get a better understanding of where you guys are coming from or where you are at in the drug development process. And I'll give everybody a couple seconds to answer those 3 questions. So I see a couple of answers coming in. Okay, a lot more answers coming in, and I'll go ahead and end it there. So it looks like we do have a good mixture. Some are already using modeling and simulation, some aren't. It's like almost 50-50. And if you've used modeling and simulation before for FIH, and again, a good mix of yes and no's. And the rat model seems to be popular. And I'll go ahead and stop sharing and pass it over to Peter.
Hi, so I'm going to just introduce our speaker today. Becky Graves is a Director of Simulation Studies at Simulations Plus, where she works on consulting projects alongside mentoring scientists, providing mechanistic absorption and physiologically based pharmacokinetic or PBPK models for the pharmaceutical industry. She uses her 10+ years of modeling experience to develop mechanistic models in various preclinical species and human populations, and to apply these to guide drug development at various stages of preclinical and clinical development. Prior to joining us at Simulations Plus, Becky also worked at GlaxoSmithKline in the UK in positions of increasing seniority within the drug metabolism and pharmacokinetics group, starting off working in the bioanalytical area and moving through to designing and managing DMPK studies to provide this strategy for various drug discovery projects. Finally, Becky moved into a team dedicated to providing end-to-end mechanistic modeling for drug discovery and development, including predicting efficacious human doses prior to first time in human studies and supporting drug product development with physiological-based biopharmaceutics modeling. So Becky's well positioned to talk to you all today on the first-in-human strategies, and I shall pass over to her now for the presentation.
Thanks very much, Peter, and hi to everyone today, and thank you very much for sparing some time to join us. I am going to just turn my video off to do the presentation because my bandwidth hasn't been so good today. Okay, so today I'm going to cover the following topics. We're going to start with a review of the literature, looking for some proof that PBPK works for first-in-human PK predictions. We'll then go on to consider the regulatory perspective before I break down the components of a PBPK model, including the uncertainty and sensitivity, and finally finish off with some model applications. But I'd like to begin by describing some overarching considerations that should be kept in mind when undertaking first-in-human PBPK modeling. Firstly, you should aim to use everything that you know, but to keep the model as simple as possible. If you can aim to use PBPK and not empirical modeling, this should allow you to combine compound-specific data with physiology, as they are intimately interconnected and explicable only by reference to the whole. Preclinical verification can increase the accuracy of the human prediction, but it will always lead to learning, and so has benefits whatever the outcome of the prediction. Always include uncertainty and never give single point estimates. And this really feeds into the next point, which is to be realistic with your expectations. A successful prediction could get the category right or within twofold, but it may not necessarily match the values exactly. And sensitivity analysis and model application can inform future decisions. And so you can apply the model to gain insight into potential development questions. And you should find that your first-in-human PBPK model outlives the duration of that clinical study specifically. So having a look at some proof that PBPK works for first-in-human predictions, there are now a number of papers in the literature that provide encouragement of the utility of PBPK modelling for first-in-human predictions. The first paper by Jones et al. Was published in 2006 and compared PBPK to the de-drift approach. They found PBPK to be more accurate for the majority of cases, and Buck et al. In 2007 evaluated PBPK for 26 clinical candidates and found that it can lead to reasonable predictions. Another paper from Jones et al. In 2011 highlighted that the simulation results using PBPK were found to be superior to those obtained via traditional one-compartment analyses, and in many cases, this difference was statistically significant. And finally, Zhang et al. In 2014 concurred with that view, stating that their prospective human PK prediction methods yielded good prediction results. So regulatory guidance from the FDA and the EMA followed in 2018, and again they supported the use of PBPK in the regulatory submissions, and more specifically, its application in first-in-human prediction. The FDA states that FIH prediction using PBPK is important for decision makers, and also that it allowed additional learning of the molecule, and that PBPK modelling may cope with situations where other methods may not be adequate. And the EMA noted that PBPK modelling is a state-of-the-art modelling tool, and that the methods used should be included in the protocol and may be summarised in the investigators' brochures. And then in 2019, as part of the GastroPlus user group, scientists from different pharma companies, together with Viera Lukachova, the Chief Science Officer for PBPK solutions within Simulations Plus, combined to publish a first-in-human modelling strategy in this paper by Miller et al. This paper includes flow diagrams for the essential components that will make up a first-in-human prediction, and these will provide the framework of the presentation today. So as already stated, a good first-in-human model should use everything you know, and the first-in-human simulator, which is a package of ADMET predictor and specific GastroPlus modules, helps you to do this. You are able to assess from structure the overall risk profile and feed that into your modelling. The simulator allows you to move seamlessly from rat through dog or any of the other more commonly used preclinical species and onto human, all within one platform. Any inputs without measured data can be predicted using ADMET predictor. And as the knowledge of your compound grows, these predictive values can be updated with measured and the model reassessed. NCA and compartmental analysis can be performed within the software, and measured or predicted metabolism data for individual enzymes can be incorporated, which in turn allows an assessment of potential gut metabolism, and using the inbuilt physiologies, you can also cover some phenotypic variability. The screenshot at the bottom of the slide here is from our standalone version of ADMET predictor and shows the results for a structure import of psilocybin. It has an ADMET risk score of 1 and an ADMET code of 3A4. ADMET risk is a drug development liability score that uses threshold values of various models to flag molecules that have potential developmental liabilities for oral administration, for example, low aqueous solubility, or in the case of psilocybin, CYP3A4 metabolism. The risk scores and their companion codes are displayed side by side, and they summarize the otherwise mind-numbing range of potential liabilities, allowing you to assess your compound quickly and easily. The risk scores for absorption, metabolism, and toxicity are also separated out to allow you to quickly focus on the specific area of interest. The artificial neural network ensemble models that are available in the standalone ADMET Predictor program can also be utilized via the ADMET Predictor module within GastroPlus. This model, again accessed via a structure import, enables you to leverage the range of predictive properties that are required for model building. Understanding these properties and determining any sensitive parameters can be key to building a fit-for-purpose PBPK model, and fits nicely with the first flow diagram in the publication, which calls out the areas that should be considered for this in silico assessment, such as compound type and the clearance mechanism. Everything that you need to do a quantitative structure property relationship, or QSPR, assessment can be found in GastroPlus following the import of a structure. Starting on the left-hand side of the flow diagram, the compound type can be accessed via the PK table, and the lipophilicity is visible on the compound tab. Here we can see an ADMET predictor import for cilostazol, which is a lipophilic molecule having a log P of approximately 3 and is essentially neutral at physiological pH, as can be seen from the predicted pKa's here. The solubility versus pH plot indicates that the lowest solubility of 0.17 mg per ml will be at low pH, and at pHs above 12, that solubility increases dramatically. Moving across the flow diagram to the BCS and ECCS assessment, the predicted aqueous solubility is displayed on the interface, along with the dose amount. The bile salt effect is accessed from the biorelevant solubilities button. And for this example, you can see that there is predicted to be no enhancement of solubility in the presence of bile salts. The predicted permeability is also displayed on the interface. And with a PEF of 3.93, we can consider cilostazol a high permeability compound, considering the cutoff between low and high permeability as based on metoprolol is about 1.2. The traffic lights buttons that you can see on the right-hand side of the interface here can also be used to infer a prediction of the BCS. The color in the text boxes for dose number, absorption number, and dissolution number change depend on the physicochemical and biopharmaceutical properties of the drug, as well as the dose selected. The color goes from green to red approximately when a drug molecule is likely to change to a different one of the 4 biopharmaceutical classification system, or BCS categories. For example, all green indicates high solubility and high permeability, along with rapid dissolution. A red dose number and a green absorption number, as we see here, indicates low solubility and high permeability, and so the compound is likely to be a BCS class 2 if the dose used is 100 milligrams. These categories are not perfect cutoffs for the BCS as defined by the FDA, but they do correctly represent most drugs. The ECCS prediction and the available transporter substrate classification models are found in the notes. For cilostazol, we can see that the major clearance mechanism is predicted to be metabolism, and also that the compound is predicted to be an OATP 1B1 substrate with a confidence of 99%. In addition to the ECCS, we have developed a Simulations Plus clearance classification system based on our QSPR models. When the category differs between the two systems, we've observed, via comparison with ADME study results from multiple contract studies, that the Simulation Plus classification is often correct. The Simulation Plus classification results are shown in the notes right next to the ECCS, and you can see in this instance that the two are in agreement and that they both predict metabolism to be the major route of clearance. Finally, looking at the pharmacokinetics tab of the interface, you can get an idea of the predicted volume of distribution and clearance. The volume can either be predicted using an ADMET predictor model that predicts compartmental volume of distribution at steady state, or via the use of PBPK, which you can see on the left-hand side screenshot. For this example, the QSPR model gives a volume of distribution of 0.89 litres per kilogram. And the PBPK model gives a volume of distribution of about 230 litres, or a 2.7 litres per kilogram for an 85.53 kilogram person. So these two values are quite different. And this highlights the differences you can see between a 2D structure property model and what happens when you predict the individual properties and use them within an equation to predict mechanistically the volume of distribution, and that takes into account the physiology of the subject. There are multiple options available to predict the clearance of your molecule, including human, mouse, and rat liver microsome predictions, and predictions from human, mouse, and rat hepatocytes, human recombinant P450 predictions, and finally a model that combines human recombinant P450 predictions for the majority of isoforms with the HLM prediction specifically for 3A4. And so you can have a look at the range of predictions that you see. And if they're all in the same category, then that's definitely a good thing. At this stage, we can run a simple simulation to determine the likely rate limiting process for absorption. In this case, the amount dissolved indicated by the red line is equivalent to the entire dose. And there is a slight space between it and the amount absorbed, which is indicated by the cyan line at very early time points, which suggests that although absorption is complete, permeability is the rate limiting step for the absorption of this compound. So once you have a feel for your molecule and the lightly sensitive parameters, you can move on to inputting your measured data. The first PK parameter we will aim to model will be the volume of distribution, as this will enable certain parameters that feed into the KP equations to be determined. Commonly available data that we will use for this task include log P, pKa, fraction unbound in plasma, and the blood-to-plasma ratio, all of which feed into the KP equations, which is set to the Lukakova equation by default. We'll also use IV preclinical PK data to rank the success of our prediction. If you copy your ADMET predictor record, you will always have the predicted parameters for reference and for comparison with any measured data that you generate. And you can start to input your measured data into the copy. It's advisable to set up one record per preclinical species and also per dose administration in each preclinical species. The PK Plus module, which is included as part of the FIH Simulator, can be used to calculate the NCA parameters from observed IV data. The NCA clearance can be used at this stage to enable a focus on the distribution. Renal clearance, as predicted by species-specific unbound glomerular filtration, can be subtracted from the total NCA clearance to enable the entry of hepatic clearance into the model. The NCA volume of distribution will provide the value you are aiming to match with the PBPK model. As an aside, PK Plus also fits a compartmental model to the IV data, which can also be used, but which will provide a less mechanistic model for human, and you'll find it more difficult to scale to human and also to implement the learnings from your preclinical verification. But there are certain scenarios where an IV compartmental model has distinct advantages in the model building process, and we will cover one of those later on in the presentation. So if we consider the initial simulation for tobramycin using mainly predicted parameters, you can see that it gives a volume of distribution that's too large. and this causes a rapid distribution to tissues and a slow return to the systemic circulation. This is where knowing your compound can guide your modelling strategy. From the QSPR assessment, we will have found out that tobramycin is a low permeability compound. And so, as we have no measured blood to plasma ratio, we can set this to 1 minus the hematocrit. We can use a permeability limited tissue model to decrease the predicted volume, and we can use a specific PSTC to try and model the volume of distribution in rats. The specific PSTC accounts for distribution from the extracellular to the intracellular space of a permeability limited tissue. And we can aim to fit these values in one preclinical species, which will allow us to verify them in others. So the results of these adjustments can be seen. So this was our original simulation. And once we've made the adjustments, we can see that the volume of distribution is much better predicted compared to the original input parameters. If we use the same strategy in the dog, again, the volume of distribution is reasonable. And in the table below, you can see the observed volume of distribution for each species, the predicted one, and then the fold error. Both of these predictions are within twofold and therefore acceptable for the model we're trying to build. I should say that the observed data is represented by the open squares in each of these plots, and the predicted plasma concentration is shown by the solid blue line. So once we are happy with our model for distribution in the preclinical species, we can return to the flowchart to determine where we've landed and what our strategy should therefore be for human. In this case, we couldn't use the Lukacheva tissue to plasma partition method with our measured input data because we over-predicted the passive distribution. So we came down the right-hand side of this flow diagram. We didn't have QWBA data. And so again, we are now down here into this box where our permeability was low. And so we tried a permeability limited tissue model with a specific PSTC. And as this did work, we can therefore use these parameters and this method of predicting the volume of distribution in human. It does note that we may wish to consider measuring concentrations in tissues of interest, as transporters may be playing a role with this type of compound. So moving on to the metabolism and elimination, here we will consider each potential process in turn as listed in the flowchart. So we have metabolism, renal elimination, and biliary elimination to consider. And we can use the available data to combine them into our model. So data commonly available at this stage includes the renal clearance prediction from IV studies, observed or in vitro biliary clearance data, and microsomal hepatocyte or enzyme kinetic data or predictions. So the first thing we can do is validate the renal clearance prediction. We can adjust the renal clearance settings in the kidney tissue to account for active processes. And there are also other predictions methods available if the FEP times GFR method doesn't work. For example, we could try using a fraction of kidney blood flow and use the same fraction across the species and see if it predicts across the species before applying it to human. In addition, the apical PSTC here can be adjusted to take account of any reabsorption that we may see. Biliary clearance data can be parameterized in a number of different ways. For example, via the specific transporter, if that is known, or as a fraction of hepatic clearance. The metabolism and transport module can be used to assess the in vitro to in vivo correlation of any in vitro clearance data that you may have. And it will also enable you to scale your in vitro clearance data to a hepatic clearance. So if you have measured clearance in rat hepatocytes, you can enter this and the program will scale it to unbound intrinsic clearance before using the well-stirred model to calculate total in vivo hepatic clearance. We have a number of options for the fraction unbound in the incubation based on the equations derived by Austin or Halifax, or using FU plasma as a surrogate for the FU incubation, or you can input measured data here by switching the input to user defined. It should be noted here that the value used on the slide is an assumed value and is for illustrative purposes only. Once you have all the component parts, the total clearance can be reality checked against the NCA clearance data. Again, revisiting your flowchart at the end of this step can help to crystallize your approach for human. And if you have no in vitro in vivo correlation to help guide your predictions of hepatic clearance, then you could consider empirical methods. For example, liver blood flow scaling or single species allometry, alongside scaling up human microsomal or hepatocyte data to give a likely range of clearance values that you can then test in your model. And again, it will give you a range of predictions to take forward for discussion. So now that we have a baseline IV model, we can build on the oral absorption component. Some of the points in this flow diagram have already been considered in terms of considering the likely sensitive parameters, but now is the time to use the PSA run mode in the first-in-human simulator to really get a handle on some of these aspects. So for this example, we're going to return to cilostazol. As a reminder, cilostazol is moderately lipophilic, essentially neutral at physiological pH. It has low to moderate solubility and reasonable permeability, and we predict to have a low bile salt effect. We have dog oral PK data that we can use for this example. So the first thing that we had to do was set up an IV model. And this is one of the occasions where a compartmental distribution and NCA clearance can really be leveraged to enable the oral absorption to be the focus, because you've stripped away any potential variability from your PBPK model. And then we can input our available measured data. When we do this, you can see from the plasma concentration versus time plot that the exposure following a 10 mg/kg oral dose to the dog is under predicted. Again, the blue squares indicate the observed plasma concentrations, complete with error bars, and the blue line shows the simulated plasma concentrations. Assessing the amount dissolved, as indicated by the red curve and red off the right-hand axis, and the blue line, and the cyan curve, which shows you the amount absorbed, we can see that the dissolution is the rate limiting process for absorption, as all of the dissolved drug is absorbed. Assessing the sensitive parameters could give an insight into which of the components of dissolution are required to fit the model, and it could also guide the generation of additional measured data if required. So here you can see we've set up a PSA, or a parameter sensitivity analysis within GastroPlus. I've picked 3 different properties: permeability, the drug particle radius, and the reference solubility, and set the lower and upper bounds to be tested around the baseline values that are already included in the model. We're going to look at 10 different values for each parameter. The results are shown in these plots below. The change in the parameter being assessed is shown on the x-axis, with permeability indicated by the red line, mean drug particle radius indicated by the blue line, with the values read off the blue axes, and solubility indicated by the brown line. On the y-axis of the left-hand plot, we have % absorbed, and on the y-axis of the right-hand plot, we have Cmax. Both of these are obviously simulated parameters. So for this compound, if the pKa's or pH solubility profile are not available, you may wish to consider measuring them, as solubility is a sensitive parameter, and you can see that it changes both the Cmax and the percent absorbed. The permeability is less sensitive as the red line is almost flat. And this is as expected considering the previous plot, and so a predictive value in this case may suffice. The particle size is also somewhat sensitive, and if we consider the baseline value of 25 micron, which is the default particle size in GastroPlus, we can see that reducing it tenfold can increase the fraction absorbed from approximately 5% up to approximately 20%, and it also has an impact on Cmax. So feeding these findings into the prediction, the solubility and permeability are measured and already included in the model. And so measured particle size data is probably where we want to look first. We do have the measured particle size data for this input material, and so it needs to be incorporated into the model by fitting a distribution to the XD50 data and resimulating our prediction. We can do this within GastroPlus by using either the XD or these XD10, 50 and 90, although please note that the input is actually radius, or even a full particle size distribution. You can then fit either a normal or a log normal distribution and save that along with the number of bins that you wish to use in the simulation. So I've used the log normal as indicated by the black line along with 8 bins, and this gives me a mean particle radius of about 7 microns. If we fit this to now resimulate, you can see that this does improve the prediction and enables the data to be simulated within the bounds of the observed data. However, confirming this with different formulations or dose levels or species is advisable before you take this input into a first-in-human prediction. So if we revisit the flowchart at this point, it indicates that requesting information around the target particle size in the first-in-human formulation will be important for the prediction. If this isn't available, then performing the prediction with an optimal but realistic particle size and communicating that as an assumed sensitive input parameter is essential. Going on now to assess gut wall metabolism. In the absence of measured enzyme kinetics, a mixture of predicted properties and human predicted clearance can be used. Data that can be used for this assessment is metabolism data, the prediction from the human clearance, the prediction of the human clearance that we have obtained from our preclinical modeling to date, and also the isoforms involved in the metabolism. And this can either come from ADMET Predictor or from in vitro data. And you can see an example of the enzyme table that contains the ADMET Predictor predictions for cilostazol on the slide. So if we stay with our cilostazol example, we can see that 3A4 is predicted to be the only isoform to metabolize the compound. And as you know, 3A4 is also present in the gut. So if we incorporate the learnings from our preclinical oral modeling, we can simulate the human profile using this RCIP predicted clearance. So from our preclinical verification, we determined that the predicted human hepatic clearance is about 40% of liver blood flow. When we consider the profile on the right-hand side of the slide, which has been generated using the predicted enzyme kinetics, the fraction escaping hepatic metabolism is about 59%, which agrees well with the clearance as predicted by preclinical verification. The amount reaching the hepatic portal vein is shown by this purpley line on the plot, and this simulation predicts that the percentage escaping gut metabolism is approximately 35%. GastroPlus also has a wealth of additional curves that you can leverage to understand your simulation further. And on this plot, you can see that the percent metabolized by 3A4 in the liver, which is shown by the brown curve, and the total percentage metabolized by CYP3A4, which is shown by the orange curve. The difference indicates the contribution of gut metabolism. So overall, this analysis indicates that gut metabolism could be impactful and therefore is a sensitive parameter for the first-in-human prediction. Again, going back to the flowchart, it indicates that requesting data to determine the contribution of gut metabolism could be advised because we believe that the compound is metabolized by enzymes, which are known to be active in the gut wall. We also know that the enzymes are expressed in the liver, but we don't know the contribution of the individual enzymes to hepatic metabolism because we've done all this from ADMET predictor inputs. So once we have all of the pieces of the prediction from the preclinical modeling, and we've confirmed these input parameters in additional species or at additional dose levels where possible, or even in just separate studies, you can pull them all together into a human prediction. The uncertainty around the key properties can then be assessed to provide additional information and a range of likely outcomes. The final flow diagram in the 2019 paper from Miller et al. Lists the properties you may wish to consider at this stage. They're grouped here into properties impacting absorption, distribution, metabolism, and elimination. As the parameters are assessed individually in a standard PSA, it is definitely worthwhile combining the two most powerful uncertain model parameters in a 3D PSA to determine the combined effect. Sometimes one property may mitigate the other. For example, low solubility may be mitigated by high permeability, setting up a concentration gradient and driving more compound into solution. Alternatively, a low fluid volume as a result of physiological variability may combine with a change in pH of a gut section to reduce the solubility and hence decrease the amount of the drug absorbed. But in addition to providing a prediction range, understanding the uncertain or sensitive parameters can also inform your clinical plan and the type of data you may wish to generate alongside the first-in-human study. So your model can help answer some of the common questions that project teams pose at this stage of development, examples of which can be seen on the slide. To assess the impact of micronization, the particle size can be adjusted in the model and the simulation rerun to assess the impact. Knowing the confidence in the clearance prediction can determine whether an IV microdose may be of use. And the inbuilt physiologies that describe the fed state can be used to determine the impact of food really easily within GastroPlus. The pH of the stomach can be adjusted to mimic the co-administration of your drug with protein pump inhibitors or other acid-reducing agents, and the risks around any data gaps can be reviewed. The model you have built to enable a first-in-human prediction can also be expanded to provide additional learnings. For example, modeling high-dose PK data in preclinical species enables the model to be used to predict the required toxicology dose amounts and regimens. This can aid in the design of these pivotal supporting studies to ensure the best chance of achieving safety cover for your desired or planned first-in-human dose regimen. Predicting the PK in the target population in addition to human healthy volunteers can also inform the clinical plan. Populations available in the first-in-human simulator include male and female, American and Asian, infant and pediatric, healthy, obese, as well as hepatically and renally impaired. But in addition, you can also edit any of these inbuilt populations to create your own customized physiology to reflect the disease or the condition of interest to you and to your model. Finally, moving beyond the modules contained within the first-in-human simulator can allow the assessment of DDIs and autoinduction. Your compound, acting as either a perpetrator or a victim, can be combined with any of our DDI standard model compounds to predict the impact of one on the PK of another. These standard compounds have recently been expanded to include some of the compounds listed as model substrates or inhibitors for enzymes and transporters in the FDA M12 guidelines. The first-in-human model can also provide the base model for exploration of additional dosage routes, for example, to enable you to administer your compound via inhalation or as a long-acting injectable within your simulation. And in terms of real-world data regarding regulatory submissions, this slide is provided courtesy of our President of Regulatory Strategies, Sandra Suarez-Sharp, and displays data we have obtained from a survey she conducted. 31 organisations responded regarding how they had utilised GastroPlus for regulatory applications, and as you can see, dose selection for first-in-human came joint first. So the precedent is set and the regulatory agencies are already used to seeing models like these being submitted as part of the package. So to sum up, aim to use everything that you know, but keep the model as simple as possible. Preclinical verification can increase the accuracy of the human prediction, but it will also always lead to learning. Always include uncertainty, but be realistic with your expectations. And sensitivity analysis and model application can inform future decisions and can give your model life beyond that of a first-in-human clinical study. So thanks very much for listening. And I think now we may go to another poll question before we deal with some of your questions.
Yep, thank you, Becky. So I have a second poll, and the question is, are you interested in learning more about how we can help your FIH strategy? And then I'll give everybody a couple seconds before we head to the Q&A. And I'll go ahead and end it there and pass it off to Peter for the Q&A.
Thanks, Jasmine, and thanks, Becky, for a great webinar. Please do feel free to put any questions into the chat or the Q&A box. Happy to answer questions that come in. I would also remind or let everyone know that if you haven't seen it, if you go to the webinar chat function, Jasmine's also put the links to all of the documents and the publications that Becky mentioned in her presentation. So please do take a look there if you've got specific need to look at any of the documents. And as I say, please type the questions into the Q&A box and we shall get through them. So the first question we've got, Becky, it goes back to, I think, earlier in the presentation where you talked about compartmental versus PBK models. And the question is, the volume of distribution is much lower in compartmental when compared to the PBK model. And is there a reason for this?
Yeah, so I think that if you consider the TD structure-based compartmental model, that's from a neural network model. Whereas once you start to look at a PBPK model, you are predicting the components of that model, like plasma protein binding, blood to plasma ratio, pKa's, and log P, and feeding those into the mechanistic equation. So the PBPK model prediction actually can pick up specific binding interactions that maybe the QSPR model misses. So in this case, because of the lipophilicity, we're probably picking up additional binding motifs that we're just not seeing in that QSPR model. Hopefully that answers the question.
Great, thanks, Becky. And I guess you probably answered that now then in what you just said, but there was another question just asking if we can predict plasma protein binding in ADMET. Yes,
we can, and not just for human either. We can also predict it for mouse and rat, I believe, at the moment.
Thank you. There's another one actually, I guess, linked from ADMET through to the PBK model. There was a question about when you go for a regulatory filing for a drug, does the FDA accept using predicted data rather than having to go and generate experimental data, and do we have experience of that?
I think a number of the models that I know I've built that have gone into regulatory filing and been accepted have had a mixture of properties. And as part of the model build, we always do a sensitivity analysis. So I would imagine that the FDA or the regulatory agencies are more comfortable in accepting predicted parameters where you can demonstrate that those parameters, that changes in those parameters don't have a massive impact on your on your prediction. Whereas I think if they thought a small change in that property could have a massive impact on the exposure that you're predicting, they would probably ask for it to be measured. But as I've said, we have submitted models with a mixture of measured and predicted properties.
Thank you. So we have another question you mentioned about additional dosage routes, and a question around whether we can predict the drug concentration in the brain after a nasal administration route.
So we can administer in the model via a nasal administration, I believe. And yes, the brain is one of the tissues that's covered by the PBPK model. You would probably have to have a look at brain predictions from a steady state PK study to qualify those, the KP, for example, but also any impact of transporters in that tissue before you went ahead and looked at the nasal dosing. But yes, in theory, it should be possible.
Thanks, Becky. And there's two questions that have come in, I think, that go sort of together, really. There's the first question is, what can be done if you have drugs that have limited clinical data? And as a follow-on to that, when you do generate first-in-human clinical data or cohort data, how do you update or challenge your previous PBK model if needed?
Yeah, so you don't need any clinical data to do a first-in-human prediction. Some preclinical data is required, but again, that could be quite limited if necessary. If you have a reasonable handle on the properties of your drug. And we actually have a really nice example of a project ongoing at the moment where the model was built just prior to the data being available from the first-in-human first cohort. And so what we're actually doing live for this particular client is feeding that data back into the model and then adjusting the model if required, and then re-predicting subsequent cohorts, including a food effect study and I believe a DDI study as well. And so that's like a real life test of our model, which is incredibly interesting. But yeah, sometimes we do need to change. But again, because of the wealth of information available from your model, it's relatively informative, and therefore you can look at all of the different curves and really get a handle on maybe which piece the preclinical verification did not allow you to predict in human, whether it's volume or whether it's clearance or whether it's something that you've missed in the absorption that's human specific, and then feed those learnings back in to get a model with more confidence in it, and then go on and predict ahead of time subsequent dosing cohorts to build that confidence and really help you to sell that model and use that model going forward.
Thanks, Becky. Another question around whether you'd recommend using population PK generator, I guess PBK plus, to give a representation of the likely variability for a first-in-human cohort.
I'm not sure if you mean pop PK
no,
or
I think
whether it's a population
I think,
simulation.
Yeah.
So you can do a population simulation really easily. And if you are worried about say, a phenotypic, if your compound is thought to be metabolized by an enzyme that has large variability, then perhaps that could be an option. But generally, I think at this stage, with all the other uncertainties that are in the model, it's as well just to do an uncertainty analysis and a sensitivity analysis and then build a range of predictions from that, because you'll probably find that that covers the variability that you see in a first-in-human population anyway, given that they're kind of healthy volunteers. And then really do your population simulations when you have a bit more knowledge of that clinical PK. So after that first cohort perhaps has come out.
Thanks. So going into, I guess, some of the slides you show on entering clearance data into the simulator, there's a question around what's the difference between adding clearance HEP information directly into the pharmacokinetic data or including Vmax and Km information in the enzyme tab. Is there a difference, or is there a difference that they should be considering?
Yeah, so that's a really good question, actually. So if you type your clearance into the liver box on the PBPK model, it will be linear clearance. If you enter a Vmax and Km, it will take account of the expression of that individual enzyme in any tissue where we have expression data in the PBPK model. So, potentially liver and kidney being the most common. And also it will take into account the Km and hence any saturation. So if you know that you're likely to have, or that you've seen a change in exposure with a change in dose, you may wish to consider switching your linear clearance model, which is where we generally tend to start with first-in-human predictions, to a non-linear clearance model that uses the individual isoforms, or at least uses the major clearance enzyme and implements a Km and Vmax that allows you to capture that clearance.
Thank you. So just a nice comment / question. Thanks for this one. It says experience is clearly important in identifying and traversing the critical path to a great model, and Simulations Plus provides that assistance. Questions around curious to know if we anticipate development of a ChatGPT-like assistance to help in the future to evaluation of results by suggesting options to explore in lieu of using the decision trees. I think probably the answer is watch this space. Robert, thanks for the question, and we will see what happens in future versions. But absolutely, it's a great suggestion and something I think will be very informative for all of our users.
Yeah, it's a really exciting time, and yeah, definitely discussions have started internally. So as Peter says, watch that space.
Maybe not time to fully answer this one, but there's a question around how you use transporter data in building a model. I don't know if you want to add a brief comment on that. I
can try. So yeah, I guess it's kind of similar to the way you'd use enzyme kinetic data. So if you know that your if you know that your compound is a substrate for a transporter, we do have some expression data in some tissues for some transporters within the PBPK model. So therefore you're halfway there, right? If you can follow this up with, if you don't have the individual transporter kinetics, you can follow this up with tissue distribution studies. And again, don't have to be radio labeled, can simply be a steady state infusion PK study where you take different tissues out at steady state and generate the KP, because this will allow you to infer whether you've got transporter activity, and then you could perhaps fit that transporter activity to those different tissues. Scaling that up to human, or making the leap between potentially a rodent to human, involves the knowledge of the expression of that transporter between those two species. And then you have to make the big assumption that the Km and the Vmax are comparable. So it is a huge assumption, and it is kind of an area that we are actively working in to try and make that process a bit slicker. But again, at the moment, it's all around using clinical data to test those modelling assumptions as the compound progresses down the development track. So again, that was a bit of a not very in-depth answer, but you can definitely use it, and a lot of it is around hypothesis testing, I think.
Yeah, and probably a whole other webinar topic to follow up on.
Possibly.
There's been a couple, probably got time for maybe one or two more questions. There's been a lot come in, so thank you. Just a couple on additional dosage routes I think have been of interest. How would you predict concentrations in the eye? Do we add an additional compartment, and how we handle that?
So we actually have an ocular model. So you can either dose to the eye and predict concentrations in the eye, or you can dose orally and predict concentrations in the eye with this model. So I think there was also a request for literature. So maybe we can follow up with that person after, because there will be literature. But as a starting point, if you want to Google Maxime Lemerdy, he has published a number of papers on how we do that within GastroPlus. So that would be a good starting point. But I'm sure we can follow up a bit more specifically if it's of interest to you.
Yeah, and I think if you take a look on our on the Simulations Plus website, there's a resource center which has a lot of our papers and posters on there, linked there. So take a look on there and search for it. You'll see a lot on there as well. I think probably we're coming to the end of the time we have. There was a question around workshops. Again, if you want to take a look on our events page on the website, they're on there. They are all in-person online workshops. We don't have any specific longer advanced workshops in person yet, but thanks for the feedback, and we are working on opportunities to get back out there and do in-person workshops. There are a couple of one-day workshops coming up in the next coming few months, which will be actually looking at the new version of GastroPlus GPX, which we're launching this year. They will be available to attend, I believe, on the East Coast and the West Coast. So look out for news of those as they come in May and June if you're looking at getting some in-person hands-on training. But thank you again, Becky, for answering all the questions in your presentation today, and I'll hand back to Jasmine for the conclusion.
Thank you all. For any questions that we were unable to answer live today, someone from our business development team will reach out to you with answers following the webinar. As mentioned, if you want to find out more about our FIH capabilities, you can visit us online. We also have 2 upcoming webinars, one on DDIs and another one on model-informed precision dosing. We invite you to join us for those. I also put a couple links in the chat if you'd like to follow us on social. And then I wanted to let you know that this webinar has been recorded for playback and will be available on our website and YouTube channel. This concludes our webinar for today. Thank you again.